So what are we going to talk to you about today? Well, obviously we're going to start with a little recap of what we've been talking about lately. But we will also talk about testing a main question. So you guys already know how you formulate a main question and how you set up an experiment so you can actually figure out what's going on. But an important part of doing experiments is also testing your data. We will look into why you test your data and how you will test your data. We will also look at collecting data and some first steps into data analysis. Well, this should be familiar to you. Formulating a main question according to the PICO model. So that's naming a population, naming an intervention, a control, and an outcome measure. In the last lecture, I gave you an example of the effect of hands-free calling on braking time. So that's where you could also apply the PICO model. Who's the population? Well, people who drive in cars. What's the intervention? Having people call hands-free during driving. What's the control? Have people not call while driving. What's the outcome measure? Braking time. We talked about the different trademarks of bad causality and how you can use experimental methodology to counter them. I've told you about the acronym RECO-RARE, which is about reading, comparing, randomizing, and repeating, so you can make sure that only the variable you are interested in is the one that varies and the rest is kept the same. In other words, controlled. So you want to know what the effect of calling is on having an accident. You don't want to deal with all the other factors that may have an effect. And you can do this by making use of the experimental methodology. Well, for your experiment, you have to read first. Figure out what is the explanation that causes this effect. So you have to know about this beforehand, a priori, as opposed to ad hoc, right now. Think of something, why this works. You have to think about something beforehand. Why will this work? Then you have to compare. In this case, we talked about using a driving simulator so you can control all the environmental possibilities. We talked about having a scripted call so that the content of the call is always the same. It's not different for different participants. And we talked about measuring brake time as an indicator of accidents. We also talked about randomization by tossing a coin, something with a 50-50 chance to randomize people across groups. We talked about why that's important. We also talked about why this is important, why it is important to repeat this more than 40 times. If you have a group of 80 people, 40 go in one group, 40 in another group. If you have at least 40 in each group, your randomization, your repetition of the randomization will allow you to control all the variables that are a part of the participants. Age, driving skill, etc. will not affect the outcomes because they are randomly and evenly, more or less, divided across both groups. We've also talked about sampling, where you take a part of the whole population and you measure these people and then generalize from the sample to the population. So you say something about the people you measured, but you also say something about the population they're from. In an ideal experiment, you randomize twice. So first, you take a random sample out of the population, and then you randomize that random sample across two groups. This way, you have a representative sample that's evenly, and all their attributes are evenly divided across two groups. So there can be no effect whatsoever except the thing that you are interested in, except an effect of your intervention. So to summarize, we're doing an experiment to find out whether A or B works better. We've talked about the methodology, how to find out that A is better than B. Today, we will take one of the last steps, which is about testing, figuring out whether or not A is equal to B or A is not equal to B. So this is a pretty general statement, A is equal to B or A is not equal to B. What it revolves around that is the certainty that we have that this effect that we're seeing in our sample is also true for the population. In other words, can we generalize from our sample to the entire population? If what we measure is true in our experiment, does it hold up in reality for everybody? Well, in order to do this, in order to test, we need to weigh the evidence, avoid false generalizations, so mistakes, basically. We need to avoid being wrong. So related to our experiment, or methodological example, what is the effect of hands-free calling on driving? We want to test this. Now let's say we've gathered our data, and we found that in group A, they had an average break time of ½ second, and in group B, they had an average break time of 0.9 seconds. How can we be sure that the 80 participants that we measured in our experiment, that the results for these people can be generalized to all drivers? Well, we can be sure if we test, if we do statistical testing. Basically, we weigh the evidence that we have and try to generalize to the entire population. Here's a different example. You can imagine that there's a guilty person, and that guilty person, or sorry, a suspect, is brought to court. So this person can either be innocent or guilty, and the court can find this person either innocent or guilty. There are a couple of decisions here that are correct. If the person is innocent and the court finds him innocent, that is a correct decision. If the person is guilty and the court decides that this person is guilty, then that is also a correct decision. However, we get into a troubling situation when either the person is guilty and the court says he's innocent, or the person is innocent and the court says he's guilty. We call these two mistakes a false negative and false positive. There are two types of mistakes that we try to avoid. We want to avoid being wrong, which is why we test. Well, the same that holds up in court holds up for an experiment. We want to know whether or not we make the correct decision. We don't want to be wrong. So instead of saying that somebody's guilty or innocent, we make different kinds of statements. We want to know whether calling while driving leads to longer break times. And if we find a longer break time, is this true for all the drivers and not just for the drivers in our sample? If you want to use an analogy, we could say we want to say whether hands-free calling is guilty or not. Well, because that's a weird analogy, the thing that we're trying to say, to make a statement about, uses slightly different terms. But we get the same types of decisions. We can have a correct decision. Something is true in our sample. Something is true in reality, in the entire population. Or something is not true in our sample, and something is not true in the entire population. In which case, we have made correct decisions. We can also make the same mistakes, as we saw in the courtroom example. You could have a false negative mistake or a false positive mistake. With statistical testing, we use formal hypotheses to guide our thinking. In this case, we have two hypotheses. We have a null hypothesis and an alternative hypothesis. The null hypothesis is always the hypothesis that states that there is no effect. Or in other words, A is equal to B, or in terms of our example experiment, break time without calling is equal to the break time with calling. If you look at the difference between the two, then the difference would be 0. The alternative hypothesis is exactly that. It's an alternative. So it's in fact saying that there is an effect. A is not equal to B. The break time with calling is not equal to the break time without calling. So there's actually a difference between the two. So these hypotheses are the thing that we test. We evaluate all the evidence and then we figure out which of these two hypotheses is true. It's just a different way of speaking, but it's the same as the innocent versus guilty. Here we say the null hypothesis is true or the alternative hypothesis is true. Again, we want to be able to generalize from our sample to the entire population. So we want to know that stuff that we found for our 80 drivers, this difference between 0.9 and 0.5 seconds, being 0.4 seconds, we found that in our sample, so there's no denying it. But we want to make sure that this is actually also true for the whole population. So what we actually test is whether this difference is true for all drivers. So if we input that stuff from the hypothesis into our little model here, instead of innocent and guilty, we say H0 is true, or the alternative hypothesis, H1 is true. If in our experiment we say there is no difference, H0 is true, and in reality H0 is also true in the whole population, then we have made a correct decision. The same holds when we, in our experiment, say H1 is true, and in reality H1 is also true. We run into trouble again once we make mistakes, once we say the alternative hypothesis is true, while in fact, in reality, the null hypothesis is true, or vice versa. So what this boils down to for our example experiment is something like this. There is no difference versus there is a difference. If we say there is a difference, and in fact there is a difference for the whole population, then we've made a correct decision. But if we mix up the two, if we say there's a difference and in reality there is no difference, or vice versa, then we make these mistakes, the false positive and the false negative mistake. So the thing we do for testing, which is super important, is first of all, we assume that the null hypothesis is true. It's always something we assume, that's a given. Then we calculate the chance, the probability, that we would find our data given that H0 is true. If that chance is less than 5%, the null hypothesis is probably not true, which means that the alternative hypothesis is probably true. In our example experiment, this means that we assume that there is no difference. After that, we calculate the chance of finding a difference of 0.4 seconds when in fact we expect there being a difference of 0. So we assume H0 is true, there is no difference. So if we subtract the two values, the difference should be 0. Instead, we find 0.4. We want to know what the probability is of finding the 0.4. Well, we in fact believe that the difference is 0. Well, how to calculate this? Then we get back to Research Skills 1, to your best friend, the normal distribution. You may remember it, hopefully. The normal distribution is a frequency distribution, so you can see how often a particular value occurs within a given population, how often a particular score occurs. So scores in the middle where the bump is are pretty common. It's where the mean is. Scores at the tails, at the ends, are pretty rare. You don't see these scores very often. So here's an example. Here I've plotted the probability distribution of the height of all media and entertainment management students. And you see that the mean height is about 1 meter and 75 centimeters. Most people are around that height. Some people are very tall, some people are very small, but they don't occur a lot. So this is how you read the normal distribution. We can make use of this normal distribution for our testing. Why? Well, because there are certain rules that are present within normal distributions. Because of their shape, we can make certain predictions. We can say that the blue area contains about 2/3 of all possible observations. The green plus blue contains 95% of all possible observations. Blue plus green plus yellow contains almost all observations. So if we translate this back to the length, we can say that 86% of all media and entertainment students are between 1 meter and 57.5 centimeters and 192.5 centimeters. So that's 2/3 of all the students are between these two lengths, or somewhere in between here. Only 2.5% are smaller than 1 meter 40 or taller than 2 meters and 10 centimeters. That's how we can use this distribution to make predictions. We can see what extreme lengths are and what common lengths are. Now we're going to use this given this mathematical truth, and we're going to rewrite it as a probability. So we're putting all the names of all the media and entertainment students. We put them on a little bit of paper, separate pieces of paper. We put those in a hat, and then we blindly pull one name out of the hat. The probability that that person is between, well, sort of say the standard criteria for normal length is about 2/3. So 2 out of 3 people, 2 out of 3 cards we pull from that hat will be from people that have that particular length. The chance is about 1 in 40, whether they're really, really tall or really, really small. That is what's going on. That's how you use this normal distribution when you translate it to probability. We can use this fact, this normal distribution, and this probability thinking also for testing our hypothesis in our experiment. So we can calculate actually what the probability is of finding a difference of 0.4 seconds when there in fact is no difference whatsoever. So here we have a normal distribution again. In the middle we have our expected mean. There is no difference. If we subtract the scores of both groups, we will get 0 if the null hypothesis is true. And here's the data that we found. We found that the breaking time difference was actually 0.4 seconds. We can also, because of the shape of the normal distribution, because of the laws inherent in this distribution, see what the chances are of finding this difference. We also have a criterion. This criterion is 5%. We'll talk about this later, why this criterion is actually at 5%. But for now, just accept it as a given. That's the third part of the basic structure for testing hypotheses. If the probability of finding a difference, when you expect no difference, is smaller than 5%, the null hypothesis is very probably not true. So to summarize, how do we test? We first assume that there is no difference. So we assume that in our example, hands-free calling does not cause accidents. The null hypothesis is that the breaking time for calling hands-free is equal to the breaking time for not calling hands-free, and the alternative hypothesis is that the breaking time while calling hands-free is not equal to the breaking time when not calling hands-free, so just driving around. Then we calculate the probability of the difference between the both conditions when it's actually 0.4 seconds instead of 0 seconds. If this probability is less than 5%, it's very unlikely that if you call hands-free during driving, you do not cause accidents. So the inverse is actually true. If you call hands-free while driving, you can cause accidents. So let's take a little closer look for the last bit. So we all know right now you assume that you're wrong. You assume that H0 is true. Then you calculate the chance of finding the data that you found given that H0 is true. If this chance that you find, that you calculate, is actually smaller than 5%, you reject the null hypothesis. In other words, if the P is low, H0 must go. Remember that, and also we'll repeat it every time you see me for the next 4 weeks. If the chance is higher than 5%, you fail to reject H0. So that basically means the alternative hypothesis is probably true. But why should we assume that we're wrong? And why do we put our criterion at 5%? First of all, we assume that we're wrong because we can make 2 distinct errors. We can have a false negative and a false positive. The false negative is saying that a guilty person is in fact innocent. The false positive is saying that an innocent person is in fact guilty. Then I put it to you, think about which decision is worse, either condemning the innocent or acquitting the guilty. Well, we can have a moral discussion, an ethical discussion about that, but this is not a moral or an ethical class, so I'm going to give you the answer. Condemning the innocent is, of course, much worse than acquitting the guilty, especially when we're talking about death sentences. Right? Similarly, you can also falsely believe that a medicine works, which will cause millions of people to actually take the medicines, giving them false hope, side effects, and costing money. Or you can also falsely believe that a medicine doesn't work and nothing really changes. Again, we can discuss the ethical and moral implications, but I think you know which type of error is worse. So this is basically why we assume we're wrong. We use the same kind of reasoning that you use in courts of law. You are innocent until proven guilty. There is no effect until proven otherwise. We assume that we're wrong, even though we want very much to prove an effect. But that's just a thing. There's a thing called confirmation bias that happens a lot in human behavior and thinking, that you're always looking for evidence to support your own views. You don't take other views into consideration, or you denounce them. We don't want to have this particular frame of mind when we do experiments, where we're gathering evidence to support our expectation, because that will lead more easily to wrong conclusions. In fact, we're going to do the opposite. We're going to say, for our testing, we assume that there's no effect. There's nothing going on. So we won't look for evidence to support our intention. We look for evidence to support that we're wrong. So here we are again with our example. We have the reality of the situation, we have our experiment. Our experiment is the sample, the reality is the population. We have these two different errors that we can make. And the thing that you need to know is that they're also known by other names. So a false negative is also known as a type 2 error, and a false positive is also known as a type 1 error. We should be able to discern the two. What is a type 1 error? What is a type 2 error? We have already seen that we want to prevent sending innocent people to jail. We want to prevent false positives. We want to prevent type 1 errors. Those are the most grievous errors that we can make, and we don't want to make them. So in terms of hypothesis testing, in terms of statistical testing, we will always looking more at the type 1 error than the type 2 error. But you should have knowledge about both. Here's another example of these two types of errors. You can say to a man that he's pregnant. That's a false positive. That's a type 1 error. You can say to a pregnant woman that she's not pregnant. That's a false negative. That's a type 2 error. So pick the metaphor, pick the analogy that fits you. You can look at this picture and say, okay, this helps me figure out which error is which one. You can also look at the law case with the innocent person in the court, figure out that works for me, or maybe you just want the formal definition in a schematic like this. Just be aware, it's important to know the distinction, and it's important to know that we want it most of the time to prevent a type 1 error. So why 5%? Well, 5%, to give you the short answer, I'm also going to give the long answer. The short answer is that 5% is neither too narrow nor too broad. We can still find things out, and we can still be right most of the time. And that's why it's set at 5%. But basically, this is an arbitrary agreement. You can change it if you want, but the golden rule is just put it at 5%. In the same way that you need at least 40 people per group in your experiment, and you accept that as a golden rule, accept 5% as a criterion for your probability as a given. But let's say that there's a psychic, and the psychic claims to be able to predict the future, and we're going to test him. We give him a deck of cards, and we ask him to correctly predict the symbol of 24 cards that are randomly drawn from this deck, with reshuffling, of course. What would happen, or what could happen? He has all of them correct. Well, that means he's actually a psychic and can look into the future. He has about 6 correct, which means that he's guessing, because there are only 4 suits, so you should have 1 in 4 about correct if you're just guessing. But we want to know, when is somebody a psychic? Is he a psychic when he has 24 correct or more than 6 correct? At least we know it's somewhere between 6 and 24 that we should set a criterion for psychicness. But we don't know exactly where we should put it. Well, we assume obviously that there is no effect, because that's what we do. We have a null hypothesis. There's no psychic, he's just guessing. So we're going to compare his behavior with guessing behavior. So it has to be more than 6. And then we can use the normal distribution and calculate possibilities of finding particular odds, of finding particular outcomes. So let's say this person has 8 correct. What are the odds of that happening by chance? Well, apparently, you can calculate this. This is a 12% chance. So 12% of the time, if somebody is just guessing, he has 8 correct. If we increase the criterion, which move it up to 9, there's a 5% chance that somebody will have 9 correct. If we increase it all the way up to 24, the chance gets the probability is really small. And that also means that it's very likely that this person is a psychic. But you can see it's sort of a sliding scale. The closer you get to 24, the smaller the probability that he's guessing correctly. For testing, we want to do 2 things. First of all, we want to minimize the chance of a false positive without, that's the second thing, being too strict. 24 correct is too strict. You'll never find a psychic that way. Or only if you test lots and lots and lots of people. So if you test everybody on Earth, there's a probability that you will find someone who accidentally guessed everything correctly. Then we get to what is reasonable. Well, if we look at these odds, if you look at this 5% chance, that's basically a 1 in 20 shot that somebody's guessing correctly. So we would be able to find psychics. About every 20 people we measure could be, by accident, a psychic. But we would be able to find something. Instead of all the people on Earth testing them and figuring out what's going on, we would test fewer people. We could take a much smaller sample. And this is sort of the consideration you have to make. You don't want to be too strict, but you don't also want to make errors all the time. If you increase the criterion or decrease the criterion, so you make C 7 or 6 or 5 or whatever, you're increasing the chances of people being a psychic when they're just guessing. If you put a C up to 6, then you would find a psychic. If you test 4 people, you would very likely find 1 psychic among them. So you would find psychics everywhere. So that would mean that you're making actually a lot of mistakes, because all these people cannot really actually be psychics. So that's why we have this 5% criterion. It's neither too strict, nor is it too loose. It allows us to do experiments. Yes? You can do this. Yes, it has an effect. It has an effect on your outcomes. So let's go back here. Here we go. Basically, the green area you see on the chart is the probability that you find a given value. So let's say this 0.4 seconds. That you calculate a p-value. Well, you do not do this by hand. You have software to do that. But if you type in this data, you put it into SPSS, then it will give an outcome. And that outcome is something called P, which is short for probability, which corresponds with this green area there. The criteria we have is 5%. So if you have an outcome that's 4%, then you would say, oh, the P is low, H0 must go. Because the P is lower than 5%, this is our criterion, there is going to be a rejection of the null hypothesis. So there's actually something going on. It's very unlikely that we find a difference of 0.4, while in fact there is a difference of 0. So in fact, this assumption that there is no difference is false. We have to conclude that there is in fact a difference, which we've proven. If you move the criterion, so if you say I'm going to make the criterion 1%, so instead of 5%, 1%, and you find 4%, then your result is different. Because 4% is not lower than 1%, it's in fact higher than 1%, so you have a different conclusion. But that's because you're very strict. You're saying, okay, I want to be really, 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 really sure that we don't make a type 1 error. And that's the thing you have to consider when you're doing experiments, when you're doing hypothesis testing. Because of this criterion of 5%, about 1 in 20 times you're making a mistake, but you don't know when. You can only figure this out when you do more experiments that corroborate your story, that corroborate your findings. However, if you change it to 1%, then it's 1 in 100 times that you're wrong. So you're being more strict, but you're also more sure that you don't find anything by accident. But it changes the way you interpret the outcomes of your experiment. Conversely, if you increase it to 10%, you move this, then this green area gets bigger, you move it's more easy to find something, more easy to find an effect, but you're also more likely to be wrong. 1 in 10 times you're wrong, but you don't know which ones. Okay? Any other questions so far? Nope. Okey-doke. Right, different tangents. We've looked right now at what you already knew about experimental methodology, asking the right questions, using the right methodology, and now we've built on that with the build-up towards the statistical testing. So right now we discussed the general framework for testing. Assuming H0 is wrong, calculating the probability that you find your given data given that there is no difference, and comparing that to a criterion to judge whether or not your effect is present. In the next lectures, we're going to build on that further. We'll talk about the different flavors of statistical tests that we use. Each of them is unique and only usable in a certain situation. But this framework that we just discussed is true for everything. However, since this next set of 2 weeks, you're also going to be able and start collecting data, I want to also talk about other stuff. And that other stuff is, first of all, collecting data. Second, doing preliminary analyses. But first, collecting data. So right now, we're in about an hour. There is a deadline for methodology, the method section. It's a good idea before you actually start doing your experiment just to pilot test your instrument. So have a few people fill it in. Do you get the responses that you were aiming for? Or is something unclear to participants? Does it actually work? A second thing that you need to consider is that you need to randomly distribute participants across conditions. and you can use the tool on Blackboard for that. But also in this week's workshop, I will demonstrate 3 different ways of randomization. So if you want to wait with doing that, you can wait until the workshop. Or if you want to start, you can also start. It's also a good idea when collecting or starting to collect data is that you standardize your protocol. So that means you should have something that describes how you approach participants, so that every participant is approached in the same neutral way, gets the same instructions, gets the same debrief, gets the same incentives, cookies, etc., if you have any, and if you want to use informed consent or not. It's basically a paper that allows people to demonstrate that they actually voluntarily join your experiment. So that's that. Next up, what to do with your data. It's important to realize that when you gather data, you can actually do lots and lots of things with it. There are many, many different possible analyses that you can do. Only a few of those analyses are relevant, and only a few of these relevant analyses are useful. So that means, first of all, taking a look at your variables and their measurement levels. Narrow down the possible analyses until the relevant analyses. Then you should inspect your data. You can look at the numbers, like the mean and the standard deviation, the correlations, stuff like that, and then decide which analyses you should actually run. Or you can visualize. Using graphs, you can look at your data, see what it looks like, and determine whether or not it would make sense to proceed with a statistical analysis. That being said, we've talked at length now about assuming that there is no difference. If you visualize your data and you can already see in this visualization that there is no difference, then it makes no sense at all to test. You should only test when, in fact, there is a difference, which you can see. So for statistical testing, you always also start with descriptives. You start with describing your data. You start with mentioning means and standard deviations. And after that, maybe visualize them in a nice clustered bar chart, and then determine whether or not you should test. So inspect your data visually, make bar charts, histograms, box plots, scatter plots, and determine what you should inspect further. So this is a bar chart. You remember this. This is a histogram. This is a box plot. This is a scatter plot. So if you look at this, in some of these cases, it really wouldn't make sense to do an analysis. But in other cases, it does. If you look at group D, there's a big difference there. You can already spot that there is going to be a difference between the two groups under that condition. So it would make sense to determine whether this effect is not only present in your sample, but how likely it is that it's present in your population, your entire target group. So you would do a significance test. You would do a statistical test. For group E, the difference is really small. So you might not want to consider testing this further. For the histograms is something you do to inspect a particular variable. For instance, if you measure willingness to pay or any other variable with interval ratio measurement level, you can create a histogram. You can see what's going on in this particular data set. It's important that this data is then normally distributed. So it actually looks like a normal distribution with the fat part in the middle and flat tails at the end. If you have something that's not normally distributed, doesn't look like a standard histogram, but more like that one, then you should consider not proceeding with statistical testing because something weird is going on in your data. If you find something like this, talk to me during a workshop. But it's important to know these things. Don't just test everything and write everything down. Be critical of your own data. Here we see box plots. Here we can see differences across different conditions. So we have yellow and orange box plots. Yellow is for a type of acid that were given to guinea pigs, something to drink, not acid to burn them or anything. And the other thing was orange juice. And what the investigators wanted to know is the effect of different doses of vitamin C in different solutions, either the acid or the orange juice, and what the effect was on tooth length. If you visualize your data like this, you can already see where the differences are. You can see that in the large dose of vitamin C, the 2 milligram dose, there is no difference whatsoever. So it wouldn't be interesting to do a statistical test here. Whereas in the other two doses, it would make sense to test. So here we narrow down the relevant analyses to the useful analyses. And the same goes for different scatter plots. If you plot two data sets, two variables against each other, and you can see that there's sort of a linear relationship in it, then it would make sense to calculate a regression or a correlation. If there is no pattern there, it wouldn't make sense to analyze this. So use visualizations to determine or distinguish relevant from useful analyses. Another thing that you can already do based on the knowledge you have from Research Skills 1 is describe your participants. How many men did you have in your experiment? How many women? What was their average age? What was the standard deviation of their age? If you have other demographic or psychographic variables, show them and try to show them in tables. So here's an example of a particular table that shows relevant demographics, relevant measurements as a summary. So don't write this all out, just create a table and write caption to the table that highlights the important differences. Here's another example. Differences between two experimental groups on different measures. You can see that 10 different measures were included in this table. We can see the mean, the standard deviations, and the frequency of observation presented here for two different groups, foreign and national. This is how you summarize data in a table. So try to make these tables for your report as well already. The point that I'm trying to make here, if you look at these bubble, there's many possible analyses, but you can't show them all. There's many relevant analyses, you can't show them all. There's useful analyses, which you can show, and all of them, because they're useful for making your point. You have a main question and you need to answer this. You don't answer it by dumping information everywhere. You answer it by making choices, rational choices, and showing the data. This is because you have to write a report, and that report is limited in scope. If you want to become Hans Rosling, that's fine, but you won't do it during this module. So I'll leave you with this video, but not before we've talked about what we're going to do next time. So the next lecture will be about the t-test, which is a particular form of test, and it builds on the framework that we discussed just now. During the workshop, I will tell you something about randomization. You can do the quiz for this week, and we will practice with SPSS and Excel for doing preliminary analyses, so that when you get your data, you can start analyzing it immediately.
Visualize